talk about nuclear energy. We all know that it is a kind of a power plant or something that creates electricity, radiations, or even heat. But what is the exact meaning of this nuclear energy? Let's talk about first the origin of nuclear energy. The nuclear energy or nuclear power began in the 1930s when a physicist, Enrico Fermi, first showed that neutrons could split atoms. Fermi led a team around in 1942 that they achieved the first nuclear chain reaction under a stadium at the University of Chicago. This was followed by a series of milestones in the 1950s, and these are
the first electricity produced from atomic energy at Eidhouse Experimental Breeder Reactor 1 in 1951, the first nuclear power plant in the city of Obninsk in the former Soviet Union in 1954, and the first commercial nuclear power plant in Shippingport, Pennsylvania in 1957.
Although even Thomas Edison opened the world's first steam-powered electricity generating station in early 1882. It is the first step to innovate such a great opportunity to the world, and good thanks to the physicist Enrico Fermi.
But what is nuclear energy?
Electricity can be generated in different ways. For example, it can be made using solar panels, burning coals, and in this, by capturing the heat from atoms that split apart. Let's make it simple. When the electricity is made from atoms splitting apart, it is called nuclear energy.
Ma'am, is the thermal power plant nuclear energy?
Well, yes.
But how about the nuclear power plants?
Well, let me explain that. At nuclear power plants, heat developed is used to make steam. Thermal power plants convert heat into electricity using steam. And to make the steam, it is created when atoms split apart, and that is called fission. When atoms split apart, they release heat.
And when the process is repeated over and over, it is called a chain reaction. Additional, in the nuclear power plant, uranium is the material used in the fission process.
The heat from fission boils water and creates a steam to turn a turbine. As the turbine spins, the generator turns and its magnetic field produces electricity. Then the electricity can then be carried to your home, so you can work on the computer, watch television, make a toast, or full charge your cell phone to play Mobile Legends. Just kidding.
So, this is the example of a steam turbine power plant. So, how it is worked?
Hello there! A steam power plant consists of a boiler, steam turbine, and a generator and other auxiliaries. The boiler generates steam at high pressure and high temperature. The steam turbine converts the heat energy of steam into mechanical energy. Then, the generator converts the mechanical energy into electric power. And electricity charges your cell phone and you can play your mobile.
Okay. So, thank you.
Let's talk about now the splitting apart of atoms, or what we call nuclear fission. As we said earlier, nuclear fission is a process when a nucleus of an atom splits into two or more smaller fragments, releasing neutrons and a lot of energy. Hence, fission is a form of elemental transmutation.
Elemental or nuclear transmutation is the conversion of one chemical element or an isotope into another chemical element, because any element or isotope of one is defined by its number of protons and neutrons in its atoms. In the atomic nucleus, nuclear transmutation occurs in any process where the number of protons or neutrons in the nucleus is changed. So, for the simple explanation, let us explain to you the nuclear fission reaction.
Unstable radioactive nuclei, which occur naturally, sometimes emit strong radiations, especially in isotopes of uranium like uranium-238 or uranium-235. The disintegration converts the uranium isotope into stable lead, and in the process emits energy in the range of 1 to 5 megaelectron volts. That's 1 to 5 million electron volts, and even higher amount of energy it can be released by breaking unstable nuclei into even more parts.
In 1939, a German scientist named Otto Hahn discovered that the breaking up the nucleus of uranium-235 into two parts emits 200 million times the energy of the neutron, which triggered it. He, along with his two colleagues Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into two equal parts.
This process is referred to as nuclear fission. So a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming highly unstable compound, nucleus uranium-236. This is what triggered the nuclear reaction.
During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and the krypton atom has 36 protons, which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons and the krypton-92 has 92 neutrons, adding up to a total of 233 neutrons.
To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equations of nuclear fission reaction taking place can be represented by this equation. So as you can see, from the equation, 1 neutron combines with uranium-235 forming an unstable compound nucleus uranium-236. This unstable nucleus splits into two stable nuclei, barium-141 and krypton-92. In addition to these two nuclei, 3 neutrons are also emitted, as well as high amount of energy denoted the equation by Q.
Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in the chain reaction as we discussed earlier. This leads to exponentially high amounts of energy being released by a single reaction. So in this explanation, we have discovered that the nuclear fission reactions result in massive amounts of energy being released.
Now, these nuclear reactions are most well known for the part they play in nuclear bombs, but they are also an essential part of nuclear reactors, which have the capability to provide the mass amounts of energy with relatively low cost.
So, that explains the splitting of atoms apart, or what we call the nuclear fission. That is part of the nuclear energy.
On the other side, let's talk about the nuclear fusion.
Nuclear fusion is the process in which a light nucleus combines into heavier nucleus and releases energy. Nuclear fusion is a lot more difficult than fission, for it has very high activation energy. An example of nuclear fusion would be the nuclei of two hydrogen isotopes fusing to form a helium nucleus. A neutron and lots of energy is also released during this time.
Let us explain to you the nuclear fusion reaction.
We will explain to you on how two or more nucleus merge or fuse together to create something more powerful and meaningful. Let's start by talking about the word nuclear fusion. Nuclear means the process which involves the nucleus and fusion. In English, means two or more entities coming together, merging together to form one single entity. So nuclear fusion can simply be defined as the fusion or combination of nuclei.
Scientifically, nuclear fission can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amount of energy. For example, lighter nuclei such as lithium and helium when combined together, we will form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is praised in terms of energy release, which is usually very enormous rather than mass.
Therefore, the law of conservation of energy is satisfied. Consider the example of two hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, one positron and one neutrino. This deuterium in turn combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, the formation of heavier helium takes place.
These three steps of a nuclear process where four protons are fused together to form a heavier helium-4 nucleus. An enormous amount of energy is a nuclear fusion reaction. Then chemical equation for these nuclear fusions is as follows. Four hydrogen nuclei when fused together give rise to the heavier helium. But how is this enormous amount of energy being liberated from just seemingly simple nuclear reaction?
For understanding this, let's first calculate the loss of mass in the process. The starting mass of the 4 protons is 4 times 1.0078, which is equal to 4.0312 atomic mass unit. But the final mass of the helium nucleus is 4.001506 atomic mass unit. Therefore, the loss of mass is 4.0312 minus 4.001506 equals to 0.0297 atomic mass unit.
This is equivalent to the energy given by Q is equal to 0.0297 AMU times 900 MeV per AMU, which is equal to 27.67 MeV. So that is the significant amount of energy released coming from the fusion of the 4 protons. However, in spite of such a substantial amount of energy being released in nuclear fusion reaction, there are no full-time nuclear reactors built so for fusion reactions, as it is a lot more difficult than fission, for it has a very high activation energy and very hard to control such enormous energy release.
So, it is clear now that the two nuclear reactions produce energy, but the applications are not the same. For fusion is a lot more several times the amount produced energy released from the fission.
Now, let us give examples of the uses of these two nuclear reactions, which is the fission and the fusion. Nuclear fission energy appears promising for space propulsion applications and in the generation of high mission velocities with less reaction mass. This is because of production of large amount of energy, around 106 times more than any chemical reactions, and can be used for the current generation of rockets.
It is generally used in radioisotope thermoelectric generators for space mission, just like the conventional thermal power stations, which generate electricity by using the thermal energy released from burning fossil fuels. Nuclear power plants follow the conversion of the energy released from nuclear fission in nuclear reactor. The heat produced during the nuclear fission removes from core by using coolant and used to generate steam, which drives a steam turbine. These steam turbines are connected to a generator to produce electricity. Nuclear technology is widely used in diagnostics and radiation treatment, like radiation therapy for cancer.
Nuclear fission is used to produce some less common radioisotopes like cesium-137 by using uranium-235, which is used in photographic sources. Nuclear fission energy is also used as a power source for propelling submarines and some type of surface vessels. Another applications of nuclear fission reactions is their high neutron fluxes, which can be used for studying the structure and properties of materials. And also, one common use of nuclear fission aside from making nuclear energy is the use of it in explosive nuclear weapons.
For the nuclear fusion, it provides a safe, clean energy source for future generations with several advantages over current fission reactors. First, abundant fuel supply. Deuterium can be readily extracted from seawater and excess tritium can be made in the fusion reactor itself from lithium, which is readily available in the earth crust. Uranium for fission is rare, and it must be mined and then enriched for use in reactors.
Second, safe. The amounts of fuel used for fusion are small compared to fission reactors. This is so that uncontrolled releases of energy do not occur. Most fusion reactors make less radiation than the natural background radiation we live within our daily lives. Clean. No combustion occurs in nuclear power, fission or fusion, so there is no air pollution. Less nuclear waste. Fusion reactors will not produce high-level nuclear waste like their fission counterparts, so disposal will be less of a problem. In addition, the waste will not be a weapons-grade nuclear materials as is the case in fission reactors.
NASA is currently looking into developing small-scale fusion reactors for powering deep space rockets. Fusion propulsion would boast an unlimited fuel supply, would be more efficient and would ultimately lead to faster rockets.
There are three types of nuclear energy. The two is already been explained, which is the nuclear fission and the nuclear fusion. The last type is the radioactive decay. So, what first is the radioactive decay?
Sir, is that a dead radio?
No! Radioactive decay is the spontaneous transformation of one radioisotope into one or more different isotopes, known as decay products or daughter products. It is accompanied by a decrease in radioactivity. This transformation takes place over a defined period of time or half-life. As a result of electron capture, fission, or the emission of alpha particles, beta particles, or photons. From the nucleus of an unstable atom, each isotope in the sequence known as a decay chain decays to the next until it forms a stable, less energetic end product. In addition, radioactive decay may refer to gamma ray and conversion electron emission, which only reduces the excitation energy of the nucleus.
One major factor affecting the stability of an atom is its size. Large atoms can emit particles to make themselves smaller. The other major factor in the stability of atomic nuclei is the ratio of neutrons to protons. The ideal ratio for stability follows the slightly curved and irregular line as shown by the dots on the graph. This ideal ratio increases as the atoms get bigger.
Large atoms can reduce their size and slightly increase the ratio of neutrons to protons by emitting an alpha particle. An alpha particle is essentially a fast-moving helium nucleus consisting of 2 protons and 2 neutrons. Taking this example of plutonium decaying to form uranium, if we write the equations out in the linear format, then notice that the equation is balanced.
The numbers on the top line, which are the nucleon numbers, add up to 240 on the left and 240 on the right. The bottom line refers to the number of protons. Note that they up to 94 both on the left and up on the right. There are two types of beta decay, most commonly beta minus, which is the emission of an electron, or beta plus, the emission of the positron.
Beta minus emission occurs when the neutron-proton ratio is too high. as in this example of radium decay. In effect, one of the neutrons in the nucleus splits to become a proton, which remains in the nucleus, and an electron which is emitted at high velocity. Again, the top line of numbers, which are the nucleon numbers, on the bottom line of numbers, which are the proton numbers, are equal on both sides of the equation.
The neutrinos, which are also emitted in this process, have very little mass and no charge. Beta plus or positron emission can occur when the neutron-proton ratio is too low. In effect, a proton spits out a positron, which the major part remaining behind as neutron. The production of positron, however, requires a significant amount of energy. Once again, examine the balance of nucleon number on both sides of each equation and proton number on both sides of the equation.
Electron captures also occurs when the number of protons in the nucleus is too high, and it requires less energy than for positron emission, as before the nuclear equation is balanced both in terms of nucleon numbers and proton numbers.
Gamma rays are very short and very high energy electromagnetic radiation. It is the former energy emitted, either accompanying or following alpha or beta radiation, and is also produced when an electron and positron mutually annihilate of itself. It makes no change to make to the structure of an isotope.
And to sum up the three, an alpha particle occurs when a large nucleus breaks down. The decaying nucleus releases 2 protons and 2 neutrons. The decaying nucleus then becomes an element with an atomic number 2 less than the original element.
Beta decay is sometimes in an unstable nucleus. A neutron decays into a proton, and that proton emits an electron. This electron is the beta particle. The beta particle is the second fastest and powerful form of radiation.
And for the last, gamma rays are electromagnetic waves that have the shortest wavelength. They are created when an alpha or beta particle is created. Gamma radiation can pass easily through most surfaces because they move at the speed of light and have no mass.
Additional radioactivity was discovered by Henry Becquerel in 1896, and also it states that radioactivity is when an unstable nucleus decays and falls apart. The Becquerel symbol BQ is the unit of radioactivity. 1 BQ is defined as the activity of a quantity of radioactive material in which one nucleus decays per second.
As there are many atoms in any substance, the decay of one nucleus per second represents a very low level of radioactivity. For more radioactive substances, or for much larger quantities, multipliers are used. 1,000 becquerels is a kilobecquerel. 1,000,000 becquerels is a megabecquerel. 1,000,000,000 becquerels is a terabecquerel. Radiation is displayed in 3 forms: alpha and beta particles, and gamma rays as we represent earlier. Here are radioactivity of some natural and other materials.
Effects in humans: Spider-Man, the Incredible Hulk, Daredevil. What do all these superheroes have in common? They all got their powers through radiation. Radiation exposure can cause all sorts of effects in real life. Scientists have discovered, sadly, that acquiring superpowers is not one of them. Alternatively, symptoms can vary from mild burns to deadly cancers.
Scientists have to consider 2 factors in order to judge the effect of radiation on a person. They have to look at how much radiation the person has been subjected to. They will need to look at how long the exposure took place, the dosage or amount of radiation received, the time over which the dose is received, the cells that are affected, the part of the body that is affected, the type of the radiation, the age and general health of the person. What are the acute effects of radiation exposure? High doses of radiation over short periods of time produce acute severe short-term effect. High doses of radiation tend to kill cells. This damages the tissues and organs. All of this can lead to a whole body response called acute radiation syndrome, or ARS. ARS can end in death. People can be exposed to high doses of radiation in a few different ways. Examples include nuclear weapon explosions, nuclear reactor accidents, and workplace accidents.
What are the chronic effects of exposure to radiation? Chronic, long-term effects may be caused by low doses of radiations over long periods of time. Low doses do not appear to cause tissues and organs to cause acute complications, but they can disrupt or change the genetic code over the long term. DNA mutations in both gametes and somatic cells. This damage can happen.
And for the protection from radiation, because exposure to high levels of ionizing radiation carries a risk, should we attempt to avoid it entirely? Even if we wanted to, this would be impossible. Radiation has always been present in the environment and in our bodies. However, we can and should minimize unnecessary exposure to significant levels of man-made radiation. Radiation is very easy to detect. There is a range of simple sensitive instruments capable of detecting minute amounts of radiation from natural and man-made sources. There are 4 ways in which people are protected from identified radiation sources.
1. Is the limiting time. For people who are exposed to radiation in addition to natural background radiation through their work, the dose is reduced and the risk of illness essentially eliminated by limiting exposure time. Second is the distance. In the same way, the heat from a fire is less farther away you are. The intensity of radiation decreases with distance from its source. Third is the shielding. Barriers of lead, concrete, or water give good protection from penetrating radiation such as gamma rays. Highly radioactive materials are therefore often stored or handled underwater or by remote control in rooms constructed of thick concrete or lined with lead. And last is the containment. Radioactive materials are confined and kept out of the environment. Radioactive isotopes for medical use, for example, are dispensed close handling facilities, while nuclear reactors operate with closed systems with multiple barriers which keep the radioactive materials contained. Rooms have a reduced air pressure so that any leaks occur into the room, not out from the room.
So we discussed about nuclear energy and its uses. Nuclear reactions, which are the fission, fusion, transmutation, nuclear decays, radioactivity, radiation, and the protection for radiation.